Okay, is everybody here? All right, it's time to get started, and projector actually works today, so we're all off and running in the right direction. So yesterday we talked about the problem of star formation, and we gave you a whirlwind tour of exactly how that works. Today we're going to talk about planet formation, and you'll see how the two interface off of each other. So let me give you a brief outline of what I would hope to talk about today, because we kind of have a full agenda. I'm going to first give you an observational landscape of what we know about planets and what we don't know, and where we are in our observational understanding of the planetary population. Then I'm going to review the circumstellar disk properties. This is the end state of the star formation problem that we talked about yesterday, and will be the beginning state of the planet formation problem that we're talking about today. Now, it turns out that there's two mechanisms to form planets. You can form them from the bottom up through a process called core accretion, and you can form them from the top down through a process of instability or gravitational instability, where they collapse all at once. And we'll compare and contrast those a little bit. Now, I'm going to argue, and I think this is correct, that the core accretion paradigm produces most of the planets that we see, and you'll see why. Along the way, I'm going to talk about a few other things if I have time. We'll talk about the extreme importance of super-Earth planets. A super-Earth is defined to be something with roughly 10 times the mass of the Earth that's mostly rocky. And then we'll talk a little bit about the late stages of core accretion, how to understand the planetary mass function, and then some organizational considerations for solar system architectures. Now, this is kind of a lot. We won't kind of finish the last couple bullet points, but we'll get as far as we can in the next hour, and then you can ask questions afterwards or this afternoon. So, starting with the following plot, which anybody who's ever seen an exoplanet talk has seen some version of this plot. So these are the planets that have been discovered to date around other stars. What we're plotting here is the mass of the planet versus the semi-major axis. And you see there's a whole host of different kinds of planets. 1 AU, where Earth is here. Here's Earth. You see that we're just barely able to be sensitive to Earth-like planets at Earth-like distances. We can see Earth-like planets further in quite easily, and we can see bigger planets further out quite easily. But this part of the diagram is not populated simply because that's hard to see. It's not that we think it's empty. Now, our solar system planets kind of live in this range here. There's a whole host of bigger, closer planets. Those are important, and they are there, but they're actually the easiest ones to see. A big planet close to the star is easy to see, so they're overrepresented in this plot. It's not that they're not important, but if you just look at this at first glance, you think, well, there's a whole bunch of things here. But this actually only corresponds to about 1% of the planet population. Another way to look at this plot is, instead of plotting mass of planet versus semi-major axis, we can plot the eccentricity of the planetary orbit versus semi-major axis, and we get this plot. Now, if you look at this plot, what you see is we have a good representation of planets all the way into quite close to the star, and we have a whole host of different values of eccentricity. Our planets, as you know, in our solar system live down here at low eccentricity, and you see that the majority of the planet population also is low eccentricity. You also see that there's a deficit of planets in the upper left corner here. There's a reason for that. If you're highly eccentric and have a small semi-major axis, that means the planet gets very close to its star. And if it gets close to a star, even if it doesn't go into the star, it gets close enough that the tidal squeezing dissipates energy, which will make the star eat the planet. So if you actually did put planets up here, they would be eaten or accreted by the star over the lifetime of the systems that we're talking about. Now, one of the things that we talked about last time was the initial mass function for stars. One of the things we'll talk about today is the initial mass function for planets. In other words, how many planets do we have of such and such mass? Well, it's actually remarkably hard to see because we don't have that many planets yet. Nonetheless, people have tried. So if I look at Jovian planets, and these are defined to be anything from about 10 times smaller than Jupiter to about 10 times bigger than Jupiter. The first such compilation was done way back in 2008. And what you find is that if you plot it in logarithmic bins, it's basically flat, with a little bit of deficit at the high mass end. So that corresponds to a power law that's almost 1 over m, maybe a little bit steeper, maybe 1 over m to the 1.3. So this was the state of the art 15 years ago. A more recent compilation shows, well, damn near the same thing. Okay, we have logarithmic bins. It's basically flat with a little bit of deficit at high mass. The slope you get is again about 1.3. So what this shows is that for the Jovian-like planets, anything from 1/10 of Jupiter to 10 times Jupiter, it's almost a 1 over m kind of mass function. Now where this fits into the bigger picture is shown here. What I'm plotting here is a mass function for all the things in the universe. Well, mostly just stars and planets, okay, not galaxies. And what we have here is the mass function for stars. Remember last time we talked about how the fact that most stars are actually smaller than the sun. The peak of this particular version of the distribution is at 0.3 solar masses. And you see there's a drop off. Now once you get to 0.3, there's a drop off on the other side. So there's actually fewer stars that aren't stars. There's fewer brown dwarfs than there are stars. Let me just remind you. This is about 100 solar masses. This is about 1 solar mass. This is about 3/10. This is the hydrogen burning limit, somewhere in here. Things to the left of this don't have enough mass to burn hydrogen, so they're not true stars. They're called brown dwarfs. And you see that when I get smaller and smaller, I go to a deficit. And then when I get to this range here, I'm in the giant planet realm. And the initial mass function I just showed you corresponds to this range here. Now, once I get below about 10 Earths, we don't know whether it goes up or goes down. This particular plot wanted to emphasize that they thought it went up, but it probably goes down. But there's a lot of uncertainty here. And that's one of the things that is sort of an open question. We'd like to know the mass function for planets at small planetary masses, okay? The other feature that we see is when we look at multi-planet systems, and these are all of the 4 planet systems that we have observed as of about 4 years ago, okay? Just because this plot is not brand new. And if you look at them, what you're seeing is the spacing of the planets, and the size of the dot or the symbol represents the mass or the radius of the planet, depending on which one's measured. But what you see is that these are remarkably uniform. The spacing is quite uniform. You can just see that with your eyes. And for any one system, the masses are pretty uniform. And if you look at this carefully enough, you see that the masses are actually uniform within the system more than they are from system to system. This has like 3 slightly bigger ones. This has 5 slightly smaller ones. There's a certain uniformity to this. You can test this statistically. Long story short is that it's statistically significant that systems within the same planetary system tend to have similar radii, and they have a well-defined spacing. Here is the spacing parameter, and it's nicely peaked at about 1 point something, okay? If I look at the period ratio distribution of all the adjacent pairs of planets, I see this plot, which is a nice, if you ignore the noise, it's a nice log normal distribution, and the colored bins represent resonance configurations. In a planetary system, there can be a very special state where the planetary orbits are in period ratios of small integers. In other words, 2 to 1 period ratio, 3 to 2 period ratio, 3 to 1, etc. So that's a special dynamical state of the system. It's actually a little bit more complicated than that. In order to be in a resonant configuration, you not only have to have the right period ratio, you also have to have the other orbital elements. Remember, there's 6 phase space variables to an orbit. You have to have all the other orbital elements in the proper configuration as well. what we're seeing here is that there's a slight seeming excess at these particular period ratios, but it's actually not a very big effect. If I zoom in and draw error bars around it, you see that this is kind of like the range from bin to bin. The only real significant excess is here. There seems to be a few systems in 3:2 beam motion resonance, and then the rest is sort of a smooth distribution. So for the rest of today, I'm going to ignore resonances. Those of you who are working on planets or want to work on planets will read that resonances are important. And they're important in the sense that there is this extra but it's only about 1% of the systems. And we're not going to talk about it further today. So what you should take away from this lattice discussion is the following. There's this certain weird uniformity that we see in the extrasolar planetary systems, particularly those that have 3 or 4 planets. This phenomena, this uniformity, is called the peas in the pod phenomena because the planets are kind of like very evenly spaced and very uniform, like a bunch of peas in a pod. It's sort of a dumb name, but that's what people call it, so that's what we'll call it. And they have the properties that they're nearly equal mass and radius, they're nearly circular, the orbits are all in the same plane, they have very regular spacing, they're basically not in mean motion resonance as we talked about, and they have small planet masses, basically bigger than Earth and smaller than Neptune. And what's not obvious, but is becoming increasingly clear as we look at more and more of the data, this is the usual state of a planetary system. These nearly uniformly spaced planetary systems. That's the natural outcome of the planetary process. One other thing is that I can divide my sample into 2 parts. I can look at the high mass planetary pairs and the low mass planetary pairs. So to be clear, what I'm doing in this plot is I'm taking all the planetary pairs in all the multiple planet systems, and I'm taking the ratio of their masses. And you see that, well, what I'm doing, I'm taking the ratio of the mass of the inner planet to the total. So if they were equal masses, there would be a peak and a half. So the low mass pairs have a nice peak and a half. But the high mass pairs are the red histogram, which is basically flat. So there's actually a difference between planetary pairs that are low mass and planetary pairs that are high mass. The difference is that the low mass ones tend to be equal mass and the high mass ones tend to be unequal mass. Now it turns out there's actually a very good reason for that, and the answer is gravity. At low mass, you don't have much gravity, so the planets are actually affected by the environment given by their host star. At high mass, the self-gravity of the planet wins, and it's energetically advantageous for each planet to try to eat all the mass while it's forming. So it's actually very natural that the high mass planetary pairs will have unequal masses, because if one ever gets ahead of the other one, it will eat all the mass and become much larger than the other one. So this is actually very understandable, but it's not obvious from the data. Next up, we want to ask the question, where do the planets live? Well, here, I don't know if you guys, I guess you guys are too young to have really seen the history of this, but let me give you a history lesson. The very first extrasolar planet was discovered in 1995. So how many of you were paying attention in 1995? You weren't paying a lot of attention in 1995. Now, what was significant about that, it was a planet called 51 Peg, which was a Jupiter in a 4-day orbit. It's called a hot Jupiter because it's hot. It's close to its star. And many of the first planets that were discovered in the late 90s, before your time, I know, were hot Jupiters. So everyone was saying, hey, most planets are hot Jupiters. We have a Jupiter, but our Jupiter is at 5 AU, and that's not hot. We're weird. Our solar system is unusual, okay? That was the bottom line. That was the party line, I guess, of what everyone was saying in the 90s and the early 2000s. Now that we have enough data and we can actually correct for the selection effects, we can plot the occurrence rate of planets as a function of either period or semi-major axis. And here's the first credible such version of that. And you see that as I go from, here's the 4-day orbit of hot Jupiters. As I go from 4 days out to thousands of days and a few AU, I get more and more planets. In other words, the peak of the planetary occurrence rate happens at 3 AU, not at 4 days. Now, since that time, there have been a few other studies, and they do this in various ways, but the peaks of these planetary occurrence rates happen at 3 or 4 AU, not at 3 or 4 days. Okay, that's very important. Now, why is that important? Okay, well, there's something very special at 3 or 4 AU. Think about it this way. What's the surface temperature of Earth? It's about 300 Kelvin. It's at a temperature where water is liquid, right? But not very much in the grand scheme of things. If we're at a typical temperature of 300 Kelvin and water freezes at 273 Kelvin, we're just a bit above the freezing point of water. It doesn't seem like that when you go outside, okay, because it seems so bloody hot. But nonetheless, we're sort of just barely above the freezing temperature of water, which means when you go from 1 AU out to 4 AU, what's going to happen? It's going to get colder. The ice is going to form. The water is going to freeze. So at a location in the circumstellar disk that's about 3 or 4 or 5 AU away from a star, there's something called the ice line. And all the planets like to form at the ice line. That's what we're seeing. Now, we actually predicted this, not me, but the astronomical community predicted this in the 1980s. And the reason is simple. When you're making a planet, the primary building blocks are the little rocky dust grains that we have invested in the gas. So planets like Earth and even the cores of giant planets are made of rocks, not gas, right? So you have to have these little rocky things that build up somehow to make your planet, okay? Now there's two important things. If you're beyond the ice line, the little rocky grains, wait for it, have ices on them because they're frozen, right? In the inner solar system, water is vapor, ammonia is vapor, CO2 is vapor. But outside the ice line, the ices can freeze out on the grains. And that does two things for you. One, it gives you 3 times more mass, which helps build things. And also, ice sticks together better than sand. If you go to the beach and you make a sand ball, it's not very fun to throw them around. But if you make snowballs, you don't have a lot of snowballs here in Taipei, but if you make snowballs, you can like throw them around because they stick together, right? So it turns out that it's a lot easier to make planets beyond the ice line. Now, why do we want to make them at the ice line instead of way far away? Because it's cold out there too. Well, the reason is that the sweet spot for making it is just barely outside the ice line. Because as you go farther and farther out, as we'll see, there's less and less surface density, so the densities are lower. Plus, the orbit time gets longer, which means the clock runs slower. And one of the things that we saw last time, and we'll see again today, is that these disks, the birthplaces of planets, do not live forever. They only live for 3 million years. So you got to do all this planet forming thing in a 3 million year time window, which is far from forever. You only get so many orbits. So the sweet spot to make a planet is as close in as you possibly can be to give you more density and more time, if you will, but still be beyond the ice line. And that's exactly where the planetary occurrence rates peak. So this actually makes a whole lot of sense, okay? So what I've done so far is I've given you sort of a whirlwind tour of 25 years of exoplanetary observations, okay? And that poses the question that we want to deal with for the rest of the talk, namely, how does a galaxy produce this weird collection of planets that we now have at least a vague understanding of? okay? And ultimately, we'd like to know their distribution of masses, their distribution of orbital elements, and unlike stars, because we were considering just one stars at a time, and stars do live in binaries, but we didn't talk about it much. Planetary systems live in groups of 4 and 5, and we have 8. We used to have 9, but now we don't have 8. But we have many, many planets. So the architecture of the planetary systems are also important. So how does this all come about? Well, it actually starts with the picture that we talked about yesterday. There's a star formation process. And we talked about star formation yesterday. Here's another updated version of the cool pictures. And why does that matter? Well, remember the star formation picture is that we somehow make molecular cloud cores, and we talked a lot about that yesterday. They collapse from inside out and form a star in the middle and a disk around it. And then somehow the star in the disk separates itself from the environment, perhaps through outflows, and we're left with a star disk system. It's when the system is in this state with a star and the disk is still there that the planets form. So what you should have taken away from yesterday's lecture that's relevant to today's lecture is that the star formation process naturally produces solar system-sized disks. And the radii of these disks is in the range of 10 to 100 AU. And we talked about a little bit of this last time, but let me re-emphasize it. There's actually a whole bunch, namely 5, independent reasons why we think the disks are 100 AU. First up, if you look at the rotation rate of the cores that we talked about yesterday, and just say, well, if they're this big and they're rotating with this much rotation rate, how far can they collapse and conserve their angular momentum? The answer you get is 10 to 100 AU. Just conservation of angular momentum gives you that. If you look at what these objects look like, at the end of the last lecture, we talked about their spectral energy distributions. And I said that the column density of the envelope determines how red the spectral energy distribution is. And if the column density is too big, the objects will be too red. Well, as you make the things rotate faster, you reduce the column density. So in order to get the column density right, you have to have the right size of centrifugal radius, which means the right size of disk, and the size of the disk that you need is tens of AU. Our own solar system has outer boundaries at 30 AU and 50 AU. Neptune's at 30 AU, which is the outside of our planetary system. But if you look at the Kuiper belt and all the objects beyond it, they continue out to about, I think, 48 AU is the canonical value. So our solar system has a size of 10 to 100 AU. There's an edge at 30 and an edge at 50. There's also the spectral energy distributions of the T-Tauri stars. Once you have the star and the disk separated from its environment, you can look at the star and the disk just by itself. And by looking at where that turns over, you can deduce the size of the disk. And I'll show you a picture in the next slide. And finally, we can actually just measure them now. The ALMA satellite just measures these things. And here's what you see. And the size of them is 100 AU. But if you look at the spectral energy distribution, and this is the spectral energy distribution of this same disk calculated 25 years before. And you see that you have all these data points. And then once you get out here, they go optically thin. So this corner here depends on how big the disk is. If the disk is bigger, the corner will be further out. But by fitting the corner, you get an estimate for how big the disk is. And for this source, the prediction was 100 AU in 1988. And when you measure it with ALMA, you get 100 AU. So all of these pieces fit together. The disks are 100 AU in size. Okay? Now, what else do we know about them? Well, here's the story. What we saw yesterday was that when you're making a star, because you have so much angular momentum, only a tiny fraction of it actually lands on the stellar surface. The vast majority of the mass that falls to a circumstellar disk, not to the stellar surface. That circumstellar disk, we've just argued, is 10 to 100 AU typically, right? The material has to somehow get from the disk onto the star, right? Now, it turns out that If the disk is too heavy, as in has too much mass relative to the star, it will be violently gravitationally unstable. Now, there's not an exact switch between stable and unstable, but there's an approximate one at 1/10 of the stellar mass. In other words, when the disk has more mass than 10% of its star, it will be violently gravitationally unstable. Now, if it's gravitationally unstable, it will adjust itself to stability through dynamical means. Dynamical means dynamically, which means the time scale depends on the orbit time. So if you have a 100 AU disk, the orbit time, Kepler's laws, tells you that the orbit time is 1,000 years. So if you have a gravitationally unstable disk, it will adjust itself to stability on a time scale of 1,000 years, right? Now remember what we learned yesterday. Yesterday we learned that stars form over a time scale of 0.1 million years, 0.2 million years, 0.3 million years. That's many hundreds of times longer than 1,000 years. So the gravitational instability time is hundreds of times shorter than the formation time. So if you ever get to the point where your disk is heavier than 10% of the star, the gravitational instabilities will set in, adjust itself to stability. But once you get to that state, so that the disk has less than 10% of the stellar mass, then gravitational instability is no longer operative, and then longer timescale processes, namely viscous friction, will set in. But that takes millions of years. So that means that when you're forming the star, you naturally have about 10% of the mass in the disk while you're making it, and then it goes down from there. So let's look at the observations. We can do this two ways. We can measure the mass accretion rates onto stars. So these are stars that are revealed but still have their disks, so they're a couple million years old, and we can look at them as different masses. If I take the mass of the star and the age of the star and say, what's the biggest m dot I can have, I will get these values. The biggest m dot that corresponds to the mass supply being 10% is this curve here. And you see that the observations, which are kind of messy, have a nice upper envelope at the 10% level. So some of them are as energetic enough to have 10% of the mass of the disks, and most of them are below that. If I ultimately don't try to measure the m dot, but rather just the mass directly, I get this plot. So again, I'm plotting the mass of the disk versus the mass of the star. The main fit is at about 1% of the stellar mass, but the upper envelope is again at this magic 10% level. So the data that we see in the T Tauri stars, the formed stars that still have their disk, show that what I just said is actually correct. Namely that the disks start with about 10% of the stellar mass, and then since they no longer have a mass supply, they only go down from there. So the disks start up here, and then as time goes down, they move down in this diagram. The disks start up here with 10% of the mass, and then they move down as time goes on. Now, how does time go on? Well, it depends on how long the disks live. So this this plot here shows how long the disks live. So what we're plotting here is the fraction of the systems that have disks as a function of time. So each dot corresponds to a star-forming region with a more or less well-defined age. And you see that the young ones have 100% of their stars have disks, almost. And by the time I get to 10 million years old, only about 10% of the stars have their disks. And you see that there's a nice downward trend that the fraction of stars that have disks goes down with time. And it goes down almost exponentially. You can fit it with a simple exponential curve. In the next plot, I'll show you just how good or how bad such a fit is. It's not perfect. Here's a couple different exponential curves with a couple different half-lives, and the half-lives are anywhere from 2 to 5, but 3 or 4 works pretty well. Point being that you can think of the disks as having an exponential distribution of lifetimes where the exponential time constant is 3 or 4 million years, okay? which means that every 3 million years you lose half your disks. So by the time you're 10 million years old, only 10% of your stars still have disks. But we know even more about the disks. We now know how big they are, they're 100 AU. We now know how long they live 1 to 10 million years with a distribution. What do their surface densities look like? Well, the surface density we can model to 0th order as a simple power law with a power law index P. Now, there are 1, 2, 3, 4, 5, 6, 7 different arguments that give you 7 different values of P. So let's go through them, okay? Yesterday, we talked about how you make a molecular cloud core, and it's centrally concentrated, and it's rotating. So that density distribution and rotation rate gives you an angular momentum distribution, right? If you take the angular momentum distribution and you convert it from the extended core state to a flat disk state, you can ask what's the distribution of angular momentum, and hence what's the distribution of mass that you need to conserve that angular momentum. That gives you a value of P of about 3/2. Okay? If you actually look at the equations that I gave you yesterday, and we didn't have time to look at them, we had solutions for how the material, the little parcels of gas, fall ballistically onto the disk. You can just put a bucket out at each radius in the disk and see how much stuff falls in each location. That will give you a power law distribution of 5/3. If you let that material adjust itself to Keplerian rotation, you get a power law distribution of 7/4. If you take the planets in our system, they're rocky or rockier than the pure solar composition. So if you add the gas back in to make it what it would have been when it was a solar nebula, you get a distribution. That distribution has a power law of 3/2. If I do that same exercise, not just for our solar system, but for all the solar systems I showed you, you get a power law index of, instead of 1.5, 1.6. If you take perfectly equal mass, equal space planets, you get a power law index of 2. If you say, what's the optimum lowest energy state accessible to those, you get a power law index just a little bit less than 2. And finally, if I look at the ALMA maps and directly measure the surface density of the gas, in the outer parts, I get a power law index that's closer to 1. So if you put all these pieces together, what you find is that the disk properties, the end state of the star formation process we talked about yesterday, and the beginning state of the planet process that we're talking about today, has the following properties. We have radial sizes of 10 to 100 AU. We have starting mass of about 1/10 of the stellar mass. They have power law surface densities with an index of 1 to 2, and they have an exponential distribution of lifetimes with a half-life or characteristic lifetime of 3 million years. So these are the environments you need or need to take into account in order to understand planet formation. Now you might worry that this is kind of a range. If you don't worry about the difference between 1 and 2, it's like, well, they're a power law with some index between 1 and 2. But we actually know a little bit more than that. They just have an index between 1 and 2, but all of the formation considerations on the previous slide give you a power law index that's close to 3/2, near the middle of that range. The ones that give you values, the arguments that give you values of power law index P close to 2, correspond to taking the rocky planets after the fact and reconstructing them. And then the one that gives you a small value of P is actually measuring the gas in the disks. So what we see is that we form the planets with a power law index of 3/2. The rocks get steeper and the gas spreads out. Now that's actually kind of easy to understand, not the exact values, but the general trend. It's easy to understand because the gas will spread outward due to viscous spreading, but the rocks will experience drag and move inward. So you make the disk with a power law index at the intermediate value, the rocks move in and get steeper, the gas spreads out and gets less steep. And that's the evolutionary trend that we're seeing in the data. So now, against this backdrop, our next order of business is to understand how the planets themselves actually form. So now we're going to finally get into the planet formation problem. And there's two ways to make planets. You can make them from the top down, and you can make them from the bottom up. When we make them from the top down, we call it gravitational instability. And the way it works is exactly like you think it works. We have a disk. It's heavy. In order for it to be gravitationally unstable, it has to be kind of as heavy as it can be at a total mass of 10% of the star or more. And when you have that, it will form beautiful spiral patterns, and some of the spiral patterns can collapse to form self-bound objects, which we could call planets. I'll talk about a little bit more of that in a minute. On the other hand, most of the metals, the things that aren't gas, in the disk start in the form of dust grains. The dust grains will quickly coagulate into basically small little rocks, basically gravel. The rocks like to be in the form of, centimeter-sized things. Things you can hold in your hand and understand, okay? Now, somehow they have to coagulate into larger things. Once they do, and we'll talk about this a little bit more in a minute, once they get to big rocks that are about 10%, or 10 times rather, the mass of Earth, the size of a super Earth, once the rocks get that big, they have enough gravity to hold on to gas. And then gas will start to accrete. And once it starts to accrete, you can make a giant planet from the bottom up. So there's two ways to make planets, top down, bottom up. Let's talk about them and see what you get. Well, here's the thing. If you take a disk that's heavy and you let it gravitationally collapse, you will get secondaries forming. This is the first such thing, I think was the first such simulation it was done back in, it was published in 92, so this was done in like 1990, so way long ago. And at the time what we were trying to do is we were trying to make binary stars out of the disk. But we could never make binaries out of the disk. What we got was instead a small condensation that's basically 10, 20, 30 Jupiters. Remember, the biggest or the smallest star you can have is at 0.08 suns, which is 80 Jupiters. Anything less than that is called a brown dwarf. So what we naturally got was a brown dwarf in the outer part of the disk. We got an object that was 10, 20, 30 Jupiters at a distance of 50 to 100 AU. Now, dial yourself forward 20 years, computers got better, and Zhao Zhu did this literally 20 years later. And what he found was that if you have the same kind of heavy disks, you get gravitational instability, and you get the formation of brown dwarfs at 50 AU. Same thing. 10 years later, Jim Stone just published a paper that has the same result. We can now actually see some of these objects. We can see objects that have masses up to 20 Jupiters. These are only about 10 Jupiters, and they have distances up to 100 AU. So here's the bottom line. If gravitational instability is operative as a way to form secondaries, what it will do is it will form brown dwarfs at 100 AU. So the imaged planets, of which these are some, there's another handful, those very well could be formed by gravitational instability. These are big things. They have masses of many times that of Jupiter, and they have distances close to the outer edge of the disk at 50 to 100 AU. They are not significantly, they are not as small as Jupiter, and they are not smaller than Jupiter. They are bigger than Jupiter, and they typically have masses of 10 or 20 Jupiters. So the gravitational instability channel of planet formation naturally produces big planets. You can call them brown dwarfs, you can call them planets. Doesn't matter what you call them, they have 20 Jupiters of mass. Maybe as small as 10, okay? So that's the summary. What does gravitational instability do? It produces brown dwarfs at 100 AU. Now, in order to do this, you need pretty massive disks, and you need efficient cooling. You have to have the right conditions. So the duty cycle of this process is probably relatively rare, but it does happen. We have some examples. But most of the planets are actually smaller than Jupiter, not bigger than Jupiter. Remember the initial mass function that we started our discussion with. It goes like 1 over m. That means there's 10 times more Jupiters than objects that have 10 times the mass of Jupiter, and there's 100 times more objects that have a mass of 1/10 of a Jupiter. And there's no way to form something as small as 1/10 of a Jupiter through gravitational instability, so we need another mechanism. Now, fortunately, we have another mechanism. And that other mechanism is called the core accretion paradigm. And the way it works, I've already briefly outlined, is that rocks accumulate into gravel. Somehow the gravel accumulates into 10 Earth mass rocks. And that's the first stage of the process. Once you get to that stage, the rock, now 10 Earth masses in mass, has enough gravity to hold on to gas. But there's a bit of a problem. As long as the gas is tenuous, it's hard to cool and it puffs up because its gravity isn't enough to compress it. And it will fill its what's called the Hill sphere. The Hill sphere is the boundary between the part of the potential that belongs to the planet, and if you go far enough away from the planet, you belong to the potential of the star instead of the planet. So there's a boundary between what belongs to the planet and what belongs to the star. We'll call that the Hill radius, and the Hill radius is actually a good approximation to that boundary. So the gas in this second stage fills the Hill radius, and then what that means operationally is that in order for the object to grow in mass, it has to cool. And that cooling takes a long time. So it takes a while. It takes a while for this object in stage 2 to accumulate mass. Now, once it gets to an atmosphere that's heavier than the rock in the middle, then the self-gravity of the atmosphere can squish it down. And then the mass can come in rapidly. And then we enter into the third stage, which we call runaway accretion. So you have these 3 stages of planet formation. Stage 1 is the building of a rock, stage 2 is the building of the atmosphere, and stage 3 is basically rapid accretion. Now, the rapid accretion occurs in the rotating frame of the planet, which means it's rotating. And if you have a rotating infall collapse, you get a disk. So one of the things that's confusing about describing this process is that there's 2 disks in play. This whole planet formation process is taking place in the circumstellar disk that's surrounding the star, but the Hill sphere collapses. This is the Hill sphere, and it's rotating, so the planet, which is way inside here, has its own disk around it. So there's a circumstellar disk that's surrounding the star, and in that circumstellar disk, the planet is forming. But while the planet's forming, there's a disk around the planet, a circumplanetary disk. So there's 2 disks that we got to keep in track. So don't be confused about which one we're talking about, okay? And just like in the star formation problem, the material that falls onto the circumstellar disk has to work its way onto the star, and then most of the material falls directly onto the disk, not onto the star, in the same way. Also, due to conservation of angular momentum, most of the material falls onto the circumplanetary disk, not directly onto the planet's surface itself. So disk accretion is once again important. To put timescales on this, we don't know exactly the timescales, but we measure them in millions of years, not surprisingly. It takes a good fraction of a million years to make the rock. It takes a couple million years or several million years for this stage 2 to happen, where the rock or the atmosphere has to build up. And then the final accretion stage takes another million years or so. What you need to keep in mind is that the second stage takes the longest amount of time, and the third stage is where most of the mass is accreted. And the first stage is where most of the rock is accreted. So each stage has its point. So what I want to do now is just go through this process in a little bit more detail. So let's talk about rocks, okay? So there's a whole bunch of different processes that make rocks. We don't have time to go through all of them, but let me give you a couple highlights, okay? So one of the things is that the rocks out in space are not hard baseball-like rocks that you know here on Earth. They're more like fluffy aggregates of rocks, so they're more fragile. And it turns out that because of that, if you have rocks that are bashing together, they will hold themselves together nicely until they get to be about this big. There's something called the meter barrier. Okay? So once rocks get to be about as big as a basketball, as big as you can hold in your hand, and they bash together, then the collisions are so violent that they tend to break apart instead of getting bigger. So rocks will naturally accumulate from little tiny dust grains into gravel, centimeter-sized things, or maybe 10 centimeter-sized things. But they don't naturally get any bigger because they start breaking apart when you smash them together. So the process that we think happens is something called the streaming instability. The streaming instability is a two-fluid instability where when you have the state where the rock's surface density and the gas surface density are comparable to each other, the gas is able to slow down the rocks enough, but there's not so much gas that it keeps the rocks from interacting. So there's a sweet spot when you have sort of equal amount of rock and gas that you can get lots of growth. That's the streaming instability. The streaming instability gives you a way to jump the meter barrier I talked about and make that gravel into little planetesimals. And planetesimals are going to be things that I'll show you next. So separately from all of this, at Michigan and actually the University of Northern Arizona and the University of Washington back in the United States, we have a collaboration to look for solar system objects in our outer solar system. It's called the DEEP survey. And we found, through this DEEP survey, 2,300 new trans-Neptunian objects. Now this little mosaic is, each one of these is a picture of one of the objects. My collaborator put them into the Michigan M just to because it's cool, or he thought it was cool. This guy Kevin did this. Anyway, these are actually pictures of 2,300 new TNOs discovered a couple years ago. Now, you don't really care what they look like in terms of this picture, but if I look at their mass distribution, I get this plot. Now, one thing that's significant about this that you don't know is that until this survey, we couldn't see anything fainter than here. So this whole real estate area is kind of new because the DEEP collaboration is actually aptly named because we can go deeper than other ones and actually measure really faint things. Now, it's a little bit subtle, but a pure power law is the purple. So purple is power law. The data go below the power law, above the power law, and then back below the power law. So that means there's a hump. The hump means there's a well-defined mass scale. The well-defined mass scale is here. That well-defined mass scale, which is measured in magnitude of observation, can be turned into a size. That size is the size you predict from the streaming instability I talked about earlier. In other words, the rocks that we see in our outer solar system, which we think are rocks left over from when the solar system was making its rocks into bigger things, have the right size distribution to be commensurate or consistent with being made by the streaming instability. So we think that what happens is that the streaming instability jumps the meter barrier and makes these rocks. Then we have two things happening. The rocks can collide with each other, and now they're big. They're not meter size, they're planetesimal size. So they're like a kilometer size. At that size, their self-gravity is strong enough to hold them together when they bash together. At the same time, there's still these little centimeter-sized things around, which we'll call pebbles. There's also, the rocks can accumulate pebbles. So through the combination of two-body big things interacting and big things eating pebbles, this field of rocky debris grows into super-Earth-sized things. Now there's actually three things that happen once you get to a mass that's kind of sort of about 10 times the mass of Earth. One is there's something called the pebble isolation mass. And that is that once you have a body that's as big as 10 Earths, and pebbles are trying to accrete, the Bernoulli equation speeds them up so much that they whiz by and you don't get any more. So you get isolated. So it's actually hard to build up an object bigger than about 10 Earth masses. The other thing that happens is that once you get to about 10 Earth masses, the gravity is strong enough that there's gas. Now, remember the composition of our disk. There's 100 times more mass in gas, at least to start with, than in rock. So as soon as the rock, in this case a 10 Earth mass rock, can eat gas, there's 100 times more stuff it has that's accessible to eating. So you're going to eat 100 times more gas than rock. So once you get to the point where you can eat the gas is going to dominate the influx, right? Now it turns out that the peak of the mass function seems to peak at about 5 to 10 Earths as well. So one of the things I'd like to leave you with is that there's actually a very important aspect to 10 Earth mass objects. And I'm going to say this very boldly. To 0th order, all of the mass in rock in the whole world, the whole galaxy, the whole universe, to 0th order is in super Earths. The amount of rock that's in bigger things and smaller things is almost not important. Now, you might think, wait a minute. We are on Earth, and Earth isn't a super Earth. And then you might think, well, wait a minute. We don't even have a super Earth in our solar system. But we do. We have a super Earth in the middle of Jupiter. We have a super Earth in the middle of Saturn. We have a super Earth in the middle of Neptune. And we have a super Earth in the middle of Uranus. In fact, Neptune and Uranus are basically super Earths with ices. If you count the ices in addition to rock, then in our solar system, there's 80 or 90 Earth masses of ice and rock in the cores of the giant planets. And in the rest of the solar system, there's Venus and Earth, which are 1 Earth mass each. So that's 2 versus 80 or 90. In other words, all of the rocky and icy stuff in our solar system is actually in the 4 giant planet cores. Earth is negligible. And if you think about Mars, Mars is 1/10 of the mass of Earth. So in the mass budget, Mars isn't even a planet. You can quote me on that. So moving on, we have the second stage where we have hydrostatic equilibrium, and then we have the third stage where we have infall. Now, I'm only going to run out of time here, so I'm going to speed up just a little bit. So let's talk about the late stages of giant planet formation. So in this late stage, we've gotten to the point where I have a super Earth, I have an atmosphere that's grown to the point where it compresses, material is falling inward. Most of the mass is accumulated during this phase. Let's see what it looks like. So the picture that you should have in mind looks like this. I have a star, and this is sort of a cutout of the disk. There's a planet that's forming here, and there's a boundary, which we call the Hill radius. Turns out there's 3 boundaries. There's the Hill radius, the Bondi radius, and the disk scale height. They're all about the same in size, but all of them sort of give you a spherical boundary surrounding your forming planet. So we can consider the material outside the sphere to belong to the star and its disk, and the material inside the sphere to be potentially forming the planet. And what you do, or what the disk does, is it sets up a flow from the circumstellar disk inside the Hill sphere. Once the material gets inside the Hill sphere, it belongs to the potential of the planet, and then it will execute orbits as given by the potential of the planet, just like the star formation problem that we saw yesterday. So the picture that you have in mind is that you have the Hill sphere, you have trajectories coming in. They're actually rotating, but I'm showing you this in projection. There's a disk that's forming around the planet. The planet's at the origin here. And then, just like yesterday, we have the analogous equations that give us the density and velocity fields. Now, you don't really care about the equations, so we can make a simplified version of them. And then around the planet, we have a disk. The disk has a surface density, and because we know where stuff is coming in and where it falls, you can calculate what the surface density of the disk looks like But again, you don't care about the details. It's going to be basically a 1 over r surface density distribution. And exactly what surface density amplitude it has depends on what the viscosity is. Even though we didn't talk about it very much yesterday, in both the planet case and the star case, there will be strong magnetic fields on the surfaces of the forming bodies. And that will inform the way material is accreted from the disk onto the planet in this case. So this is a close-up where I'm only plotting at like 4 planetary radii instead of 1,000 in the previous. So this is a zoom in, okay? So one of the things that you might care about is how the energy is generated. Well, just like yesterday when we talked about stars, the planet has intrinsic energy. It has energy from disk accretion. It has energy from disk mixing, and so on. We have analogous versions of each luminosity source that we talked about yesterday. And what that will give us is it will give us a spectral energy distribution. So the planet and its disk will have a spectral energy distribution. The material that's falling around it will then reprocess some of that and give you an envelope distribution. Now, what I'm going to do now is page you through what the spectral energy distributions of forming planets look like. So here I'm going to fix the mass accretion rate and the location of the planet to be at 5 AU, and I'll fix the inner boundary condition to have a magnetic field of 500 Gauss, and then I'll show you what happens as I make M bigger. As I make M bigger, I go from here to here to here to here to here. I get more luminous objects that become bluer. If I instead keep the mass the same and make the mass infall rate bigger, I get more and more luminosity, but it becomes redder. And if I change the magnetic field strength, I only change the details. And if I change the location of the planet by moving it closer to the star or farther from the star, I make the spectral energy distribution wider and narrower. Because when I make a planet closer to the star, the Hill radius shrinks, the disk shrinks, and I have a narrower spectral energy distribution. So, why am I telling you this? Well, we are now on the cusp of being able to look for planets in the process of being formed. Okay? Right now, there are like 3 data points. But if there's 3, that means in a decade there'll be 3,000. That's weird. We're almost done, so we'll just keep going. This is the one case where I could actually look at a forming planet. You see, this is actually a very, very late stage of the planet formation process. So these little things here are circumstellar disks that are, or circumplanetary disks rather, that are just now visible. So far where we are is we have solutions that describe the material as it falls from the circumstellar disk into the Hill sphere and onto the forming planet. We can describe the velocity fields and the density fields. We can describe the structure of the disk, and then we can construct the spectral energy distributions of these things to see what they look like. So there's one thing that I want to talk about before we, and this is a good place to end, I think. So let's compare and contrast what we learned today with what we learned yesterday, okay? So one of the things that's similar is that we have a central body, a star yesterday, a planet today. Because of conservation of angular momentum, when these things are gathering mass through gravity, they naturally accumulate disks around them. We had a circumstellar disk yesterday, and we had a circumplanetary disk today. And then while they're forming, there's an envelope of material that falls onto them, which will be the source for the mass, and will also reprocess all the radiation and determine what these objects look like when they're in the process of forming. So if you want to identify them in the sky or find their properties, this is what you need to know. But there's one important difference that I want to emphasize, and this is where we'll end. In the star formation problem, yesterday, the stars form quickly. They form in 1/10 of a million years, we'll say. Okay? And the disks are big. They're 100 AU. Now, what does that mean? The surface of a star is like 10 to the 11 centimeters. That's almost 100th of an AU. And the disk radius is 100 AU. So that's a factor of 10 to the 4 in radial scale. So when a star is forming, material falls to the disk, but it falls to an enormous radius that's 10 to the 4 times bigger than the star. And it has to somehow get from there to the stellar surface in 1/10 of a million years. Viscosity is too slow. That's why the objects become gravitationally unstable, the disks become gravitationally unstable, and gravitational torques do the transfer. In the planet formation process, planets form over a time scale of 3, 4, 5, 10 million years. That's 100 times longer in time, yeah? And the size of the disks, I didn't emphasize it, but it was on the graphs. Instead of being 10 to the 4 times bigger than the planet, they're only 100 times bigger than the planet. So that's the big difference between planet formation and star formation. In star formation, you have 100 times farther to go in terms of disk transfer and 100 times less time to do it. In the planet problem, you have 100 times shorter to go and 100 times longer to do it. So in the planet formation problem, the viscosity can easily keep up with the infall, transfer the angular momentum to the disk and onto the planet, and you're good. Whereas in the star formation problem, you have to rely on gravitational torques. So this is a good place to stop. We're out of time for today, but we have time for questions. So I just wanted to emphasize the difference. One of the things that we could talk about if we had 3 more lectures is we can talk about how to actually think about constructing the initial mass function for planets. And we can also talk about why it is that the planets tend to have these equal masses. Long story short, the answer to the last question is that you can show it's the lowest energy state accessible to a pair of forming planets to be nearly equal mass as long as the mass isn't too big. Once the mass gets too big, it becomes energetically favorable for one planet to eat all of the mass. And that driving principle actually goes a long ways towards explaining the architectures that we see of a lot of our planetary systems. But again, that's sort of a higher order detail and beyond the scope of what we could talk about today. So let me stop here and I will open the floor for questions. So there's got to be some questions. We had sort of, yes, sir. Yeah.
We use our current theory to explain the formation of like Earth-like planets, like Earth, Venus, Mars, or even.
Oh, that's a good question. So in this picture, the formation of Earth and Venus are, well, there's 2 answers to that. When you fail to make a super Earth, you end up with an Earth. So that's part of the reason. And second, if you have a low mass disk for whatever reason, so let's say that the star and the circumstellar disk are very efficient at putting material onto the star, and you end up with a very tenuous low mass disk, then what you'll tend to form is a bunch of Earths. Now we have 2 Earths, one's called Venus, and Mars is sort of a failed Earth, right? Because it's only a 1/10 as big. So we sort of have a wimpy version of that story. There's another system called TRAPPIST-1 where there's like 6 Earths that are all in a line, right? So for sufficiently low mass disks, you'll tend to have equal mass Earth-like planets. The other thing I should say is that if you look at our terrestrial planet system, so Mercury, Earth, Venus, and Mars, it's a 4-planet system. It's actually pretty equally spaced in orbits. And Venus and Earth are nicely equal spaced or equally sized in mass. You can compare that to all of the other 4-planet systems that we've discovered. And then you can rank them in order of how uniform they are. In other words, how much their masses are the same. And where we rank is sort of in the 20th percentile. And what that means specifically is that 80% of the systems are more ordered than ours, and 20% are less ordered than ours in terms of how uniform they are. So we're not outlier. We're just a little bit below average. We're like a D student, okay? In terms of how uniform our inner solar system is. Because one of the things that keeps coming up in these discussions is, well, how usual is our solar system? Well, as you're getting the idea from this discussion, there's lots of different ways to build a solar system. So the weird way to say the answer to that question is our solar system typical? I say, well, it's not typical because there's lots of different ways to make it. It's not typically going to end up ours. But at the same time, it's not atypical either. Because 20% of the time you get less uniform than our terrestrial planet system. That's not weird at all, right? The other thing that's relevant is that the peak of the giant planet occurrence rate is at 4 AU. Our giant planet, Jupiter, is at 5 AU, exactly where it's supposed to be, right? So in that sense, we're perfectly typical. Other questions?
Maybe it's just a detail I missed earlier, but about the ice line. Does it vary with the mass of the center of the star?
Yes, it does. The location of the ice line will depend on the luminosity of the star. Now, one of the things and that's important, but at the same time, it's actually not quite as strong as you think. And the reason is that we know that little stars are a lot dimmer than bigger stars. So the main sequence luminosity of a K star, for example, is quite a bit smaller than the main sequence luminosity of the sun. But remember from yesterday, the Kelvin-Helmholtz pre-main sequence contraction time is 30 million years, which means none of these stars are main sequence stars. They're all pre-main sequence stars. And the difference in luminosity with mass is much less for pre-main sequence stars than for main sequence stars. So even and also the pre-main sequence luminosity is actually bigger for all stars than their main sequence luminosities. So for that reason, the effect you're talking about is real, but it's not as big as you think. So the ice line does depend on luminosity. It also varies with time a little bit too. So it's actually not one location, but it's kind of a moving surface if you want to get into the detail of it. But in terms of broad brush strokes, it's just a line, and it's at about 4 AU.
So where is the ice line for our solar system?
It's basically just inside Jupiter. I mean, if you take the pre-main sequence luminosity of the sun and the time at the time when we think the planets were being made, the ice line is somewhere between Mars and Jupiter.
Then my second question, kind of unrelated to the first. Previously you showed a graph where you showed the stars and all the planets, all the exoplanetary systems were discovered, and on the right side there was zero mass. Can you go back to that?
So which
Plot where you were from where you concluded that most of the planets, the mass and the radii of planets are pretty much uniform.
Oh. I think I know which plot you mean. This one?
So are these are the vertical lines are those distance measurements?
Oh, well, what we're plotting here is each line is a solar system that's observed, and they have these phone numbers like this. Then for this system, there are 4 planets. The location of the planet in semi-major axis or period is given by the spacing this way, and the size of the dot is the radius of the planet. So you see that this one is pretty uniformly spaced, but these two are a little bit close, and their sizes is pretty uniform. If you go to the next one down here, you see that these are also equally spaced and equally sized, but this size is a little bit bigger than this size, and this spacing is a little bit bigger than this one. So the statement that you should take away from this is that the uniformity within the system is very high. So within a given multi-planet system, the masses are very much identical, not completely identical, but very much well correlated, and the spacing is very, very even. And the spacing and masses within the system are much more uniform than from system to system. And you can just see that in these two cases right here.
Is SOL our system?
Oh, yes. See, our system has pretty small planets, and that may or may not be unusual. It's actually pretty, as we saw, we're right at the observational cusp of being able to see planets as small as ours in other systems. So once we have 10 times more data, we'll kind of know whether there's lots of small planet systems like ours or not. But the uniformity of ours, you see the spacing is pretty good. These guys are exactly the same size. These guys are a little small. So it's not crazy in terms of uniformity, but it's not the most uniform ones either. That's why we're a 20th percentile event in this plot, right? So.
You say that we are able to tell that most of the planet will form just outside the ice line.
Well, that's just the optimum place to do it, yes.
But we have not able to detect the stars, planets like Newton, right? So there might be always more planets outside.
Yes, yeah. So let me be very, very clear. The ice line says it's, the ice line argument says that it's the best spot for making a planet is just outside the ice line. It's not the only spot. It's not the only place. We also suspect that there will be planets formed further out. In our solar system, as you go further out, the planets get smaller because they didn't have as much time to get as much mass, we think. We don't know how that will play out in other solar systems because, as you point out, we're just on the cusp of being able to get some data there. So upcoming experiments, including the microlensing things on the horizon, will give us a lot more information about just that idea. So we don't know for sure. That's what I would guess, what you said, but we don't know because we need more data. So, yes?
So for planet forming by means of gravitational instability, it was mentioned that most of them forms at around 100 AU, or essentially at the edge of the circumstellar.
Near the edge, yeah.
Yeah. But what about those that forms much nearer to the sun? What makes them different?
Well, when you do the physics, and we didn't have time to go into it, it's actually very difficult to get gravitational instability to make secondary bodies too far in. It just doesn't happen. And you can kind of see why. In order for gravitational instability to happen, gravity has to win over pressure. And in a circumstellar disk, it has to win over pressure and the Keplerian shear, which is trying to pull things apart. As you go further in the disk, it gets hotter. So the thermal pressure is bigger, and the Keplerian shear is bigger. So if you want to form it, I mean, just conceptually that makes sense. When you put in the equations, it also makes sense. Sometimes when you make the intuitive argument, there's something that's subtly wrong about it. But in this case, that actually holds up. So that it's actually impossible or very, very unlikely for gravitational stability to happen too close to the star. The sweet spot for making the gravitational instability argument work is as far out in the disk as you can go. But the disks only go out to 100 AU. There's no mass beyond that. So then the best place to make them is between 50 and 100 AU.
Because by intuition, I would think that it should be possible near the center because technically there is more mass.
Well, actually, there's not more mass. There's a bigger surface density. But remember, our surface densities, sigma goes like r to the minus 3/2. When you integrate m of r, you take r to the minus 3/2 times r dr integral. That means that the mass enclosed goes like a positive power of r, namely root r. So all the mass in the disk is on the outside, not on the inside. It's denser in the middle, but all the mass is on the outside. So that's another reason why it's favorable to make gravitational instability planets on the outside of the disk rather than the inside of the disk.
So now we are mostly talking about the single star planetary systems. So if we have binary star systems, how would it affect the type of planetary systems that we have?
Well, that's a very good question. So first of all, let me give you some numbers. Okay, the question for everybody is, what about binaries, right? What does binaries do? Well, for solar type stars, about half of the stars are binary and half of them aren't, right? That's just the way it works. So for half the time, you don't care. Now, of those the half that are binary, they come in all separations. They're sort of equally spaced logarithmically. So some of them are close binaries where the stars are within 10 stellar radii of each other. Some are at 1 AU separation, some are at 10 AU separation, some are at 100 AU separation. The peak of the binary period distribution for solar type stars is at 10 to the 5 days. What does that mean to you? That's 42 AU. 42 is the number for the answer to life, the universe, and everything. Also, it's the typical binary separation. That means that half of the binaries are wider than 42 AU. Okay? So if you're trying to make a planet like Earth at 1 AU and your binary is at 40 AU, what's going to happen? Nothing. It doesn't care. So half the binaries are wide enough. So half the stars are not binary. And half the binaries are wide enough that planet formation doesn't care. Now for the other half of the half, the quarter, the binaries are in the way. And they will shut down or influence planet formation in their vicinity. So for the binaries that have separations of 1, 10, a half AU, you will compromise terrestrial planet formation or Jovian planet formation because there'll be a big star in the way. And that will keep all of these processes that I described from happening. Now there's more. When I go from a solar type star down to a smaller star, the binary fraction decreases. And as we talked about yesterday, most stars are smaller than the sun. So when you put those two things together, most stars are smaller than the sun, and the binary fraction decreases with stellar mass. So it turns out that even though half of the solar type stars are binary, most stars in general are actually not binary. So most stars are actually single, which means it doesn't matter. And most of the binaries, at least half the binaries, are wide enough that it doesn't matter. So there is a subset of binaries that mess up planet formation, just like you're saying, but it's actually a slightly smaller fraction than you would naively think until you think about the numbers, right? That's one of the weird things about astronomy is people say, well, most stars are binary. But that's actually not true. Most stars are actually single. That doesn't mean binaries don't matter. They matter in this quarter of the cases or 20% of the cases, but for most of them, they don't. Any other questions? Or are you guys getting hungry and ready for lunch? Well, one last question.
Can you also give an insight as to why planets in binaries more often form circumstellar orbits instead of circumbinary orbits?
Well, I don't think we have enough data to say that for sure. Certainly, most of the planets in binaries that we've seen orbit one star with the binary outside. Just like I said before, the binary is far enough outside we don't care. We've gotten a few observations of close binaries with planets around them, but only a few. We don't know exactly whether that's an observational selection effect because it's harder to see those or what the statistics are. But I think in terms of the real estate we were talking about earlier, there will be more cases where the binaries are wide enough that they won't affect planet formation around one of the stars. And I think there'll just be more real estate and parameter space where that's the case than where you have close binaries with disks around them. But I don't have a lot more to tell you than that. Okay, any late breaking questions? All right, so it's almost noon. I will let you guys go, and thank you for your attention.